Let me go. So welcome everyone. My name is Lauren Scott. I'm from the CAE Program Management Office. And again, welcome to our October offering of our CAE Forum. We have two great presentations today. And our first is going to be Dr. Bruce Harmon. He is from University of Denver. So he's going to be talking about under the hood of the quantum computer. So without further ado, I will turn it over to Dr. Bruce Harmon.
Well, thank you, Lauren, and welcome all of you to this talk. I really appreciate you attending, and hopefully you pick something up that is of benefit to you. And if not, please be sure to email me after if you would like to discuss this further in any way. I'm open to all of that, of course. Under the hood of the quantum computer, then, just a little bit about me before I get started. 17 years with Hewlett-Packard, where I was a developer, software, hardware, firmware, and integrated circuits, and then leadership of small and large teams doing that. 3 years with Synopsys, the top EDA, electronic design automation supplier, making tools for integrated circuit design. 3 with Rudolph and KLA-Tencor, the top suppliers in semiconductor wafer inspection at the time, and probably still that way. One of which made macro inspection, so determining whether individual die were likely to be effective when packaged and inserted into circuits. And then KLA-Tencor with a very exciting product, ultraviolet illumination, dark field inspection of wafers to make sure that the depositions in each layer were proper. So a lot of heavy software in all of that. But the reason I'm talking is that I got very, very interested in the quantum computer some time ago, and it really began right here with a doctoral student when I was teaching, and I was a dean at Colorado Technical University. Matt Perkopile had been working on his dissertation on quantum computing, and I got very, very interested. So that was in 2009, and through the interaction, through meeting with this committee, meeting with him, I just got very, very interested. And I put together some presentations about this as a result of my own research, and have been very interested since, and have made presentations on this in some other forums. But then I kind of got rekindled as one of my students, a graduate student here at the University of Denver, where I'm a faculty director and a professor today, got very interested in this topic and is now using an independent research under my supervision at this time in the very same topic. So rekindled, I revisited what I had said before and all that has happened since, and hope that what I bring to you today is of some benefit to you. I don't want to say that I have ever used a quantum computer, but I've certainly studied the topic, and we'll see if that's useful to you. So we'll do a background, motivation, why are we here? What is quantum computing? What is the history of it? What are some of the recent developments? And then we'll get under the hood and figure out, how does this thing work? How would you program it if it existed? And that's a big if. And we'll talk about the mitigation. So why are we here? Because from a cybersecurity point of view, the quantum computer represents a possible attack vector and probable attack vector to encryption as we know it today. So the quantum computer then, if it existed, would seriously threaten the RCA encryption technique used broadly, almost universally at this point. And Peter Shor's algorithm from, I think, about 1994, somewhere around there, is the algorithm that would threaten it. It's a very detailed algorithm, and we'll talk about that in a little bit. Research has been underway in a quantum computer since the 1980s. And at this point, many people believe that there are mechanisms to realize it. And some of them involve quantum mechanical properties themselves, which is entirely consistent with how Richard Feynman originally proposed that such a thing might exist. So photon polarization and electron spin, for example, would be properties that exhibit the principal characteristics of quantum mechanics that would be relevant to a quantum computer. Several companies claim to have one, most notably D-Wave, excuse me, and IBM, but there are others as well. Google owns one. Though the urgency is because it can break encryption as we know it. So that's the fuss. D-Wave Systems in 2011 really made quite an impact, having 128 qubits. We'll talk about qubits in a bit. And this was much criticized by academics, and it was later published in Nature. You can go back and see what was being said back in those days. And then Google in 2013 bought one of those units, and IBM has a unit of its own that is of its own invention. And there are other players, as we shall see. So let's go to the history of this. It really goes back to quantum mechanics. Early in the 20th century, pioneers, especially Einstein, Bohr, Planck, Dirac, Heisenberg, and Schrödinger, were exploring this and developing new theories and running experiments and determining that this really was quite a phenomenon and very hard to understand. Central to all of this is that we cannot know both the position and the momentum of a particle. This was posed by Heisenberg, who, and it has become named the Heisenberg uncertainty principle, and essentially underlies quantum mechanics. And it's not intuitive at all. We also understand that a photon can be in two places at once, and multiple places, presumably. So digital computing itself began around the World War II era, but the notion of a quantum computer and what it could do really came about in about the 1980s, wherein Manin and Feynman famously determined that if you were going to actually use a digital computer to simulate the quantum mechanical properties that we now believe to be true, you'd need a quantum computer in order to do it. I mean, so it started like that, and evolved very much differently from that original concept. So here they were. They said, we want to be able to simulate quantum mechanics, so let's invent something that can do that. And so the concept was born from that. David Deutsch expanded upon it muchly, and then finally Peter Shor in 1994 with his famous algorithm really expanded upon it. So what they did is they said, if such a quantum computer existed for the purpose that Richard Feynman is articulating, then what would be its characteristics, and how would we go about making one? And how do we go about making one was a much more difficult question than what would its properties be. So original exploration was along the lines of what would be the properties of a quantum computer. Let's see, Heisenberg's principle, we often talk about Schrodinger's cat. This is a thought experiment in quantum mechanics that I'm going to get to in just a bit. But if we think of a particle or some other object having multiple states, and we don't know for sure which state it is in, then that's the quantum mechanical property that we want to pay attention to. And so we create something called a qubit, And a qubit then really must be in one state or another, but it has a property of being probabilistic, so that there is a certain probability it's in one state and a certain probability that it's in another. And what we're going to exploit in the quantum computer is this indeterminacy. But at some point at the end of the day, you need to measure the output and see what state it really is in. And so a measurement is what's going to collapse the final state into some real state. So entanglement is an important property too, because if we have two objects that are entangled with one another, then that's a property that can be exploited as well. And Einstein referred to this as spooky action at a distance when he made the following observation. If there were two electrons which had opposite spin and they were entangled, and you held, after they had been entangled, you held one close to you and put another one 5 galaxies away, and then you made an observation on the first one and determined which spin it had, then you knew 5 galaxies away that that one had the opposite spin. And so Einstein felt like that's not fair. You have information that traveled faster than the speed of light, when in fact others made the observation, no, you're really not interpreting that right. It's entanglement, and we haven't communicated with that thing in 5 galaxies away. We have just made note that since they were entangled at birth, we know what that result is over there. The notion of Schrodinger's cat, in case there are some of you who have not heard this, it's a thought experiment. But if a photon over here on the left is emitting, a photon generator is emitting photons into a screen with 2 slits, then on the opposite wall, there will appear an interference pattern, which can only exist if the photon was simultaneously going through both of these slots, because of the wave property of photons. It being light has the dual property, dual characteristics of being both physical, like a photon, as well as wave-like, and in the way that it can form these interference patterns. So if this is the case, that it's actually superimposed, that it's in both places at once, then which one is it going through? So a thought experiment would be, suppose one of these could lead directly into this chamber with a cat inside and trigger a Geiger counter that would then trigger poison and kill the cat, while the other one, if it was going through the other slot, would miss the Geiger counter and the cat would be alive. So it's superimposed. It's both alive and it's dead. Is a thought experiment? It's not so much a thought experiment, just a thought that how it sort of contradicts. And so it's one of these things often brought up. Well, how can quantum mechanics be true in the face of Schrodinger's cat as an analogy? But it does explain phenomenon that we have seen, and so it's an important concept. The entanglement, the superposition are the principal properties that we will be exploiting in a quantum computer. So there's the quantum computer does have quantum mechanical properties because that's the only way you can get something physical to do these things. Now, I'm going to talk about why it's a threat to the RSA and encryption as we know it, and that's a very important factor. But I do want you all to remember that it's being brought about not because it can kill RSA, it's coming about because it can do so many things. We believe theoretically possible that it can do so many things that would benefit humankind. AI and machine learning, there's articles about all of these that you can look up: computational chemistry and biology, the design of new drugs, forecasting of weather, optimization of all kinds, and financial modeling. All of these are potential application areas that have been written about in the literature, and you can expect that are reasonable targets for a quantum computer. And I do want to say that if you've ever followed the Gartner hype curve, it's of note that this year, and for the first time this year, the quantum computer appears at the bottom of the hype curve. Briefly, the hype curve is where different technologies experience a lot of hype before people begin to realize that actually they're really not up to what the hype really was telling us. And so they go through a trough of disillusionment before real people begin to really use the technology, and we end up with a plateau of productivity for a given technology over time. So all kinds of technologies, you can see it on the chart, have those that Gartner thinks are applicable going forward. But anyway, the point is that the quantum computer has reached a point of some hype that it did not experience before. So there's something to be said in getting on Gartner's radar. Quantum supremacy was announced by Google 2 years ago, and you can click on this link, you'll get access to these. I'm a little bit worried that if I click on this, I won't be able to get back, but let's see if, no, I tell you what, I'll let you click on them in the interest of time. But in this article, you will see that Google is making the claim that they have achieved quantum supremacy. And what that means is that they have now been able to demonstrate the capability of their live quantum computer to do things that would not be possible in a reasonable amount of time on a classical current generation computer. And the rationale for making that claim is that if they solve an algorithm that takes exponential time, then that can be considered intractable because when problem sizes get large enough, it cannot conclude its work in a reasonable amount of time. And that's really part of why RSA works is, you could eventually factor RSA, but it would take you so long that we wouldn't be alive when you were finished. So anyway, Google makes the claim that they have solved such an algorithm using their quantum computer, which, if we recall, was one made by D-Wave. So there are many variations now on the quantum computer as compared to when I first got interested back in 2009. The quantum circuit model, though, is the one that's most often used. But you'll note in the literature that there are other manifestations, other techniques, other ways to achieve a quantum computer that are subjects of research, as is the quantum circuit model for that matter. And by the way, you can get these slides off of the internet when all of this is done. And I would expect that you'll be able to click on the links that I provide here to further your interest in researching this topic. And again, I'm going to be available after this for an email and a potential conversation if that's something you want to do. So the exploitation that we're talking about, one of them is entanglement. We can embrace that, and that was the notion that two objects, potentially two qubits, can be entangled with one another. And it's important to show that the discrete Fourier transform is able to exploit certain properties. So just as today, we use the discrete Fourier transform and its variant, the fast Fourier transform, to gain information about signals as to the frequency composition based on properties of the interplay between the complex numbers and the periodicity of the exponential function. So if we can do that there, then the idea is there can be a quantum Fourier transform that exploits the properties of the quantum computer and the qubits in such a way that we are able to gain the advantages that the quantum computer can do. Superposition being one of those as well. A qubit can be in one of two states with different probabilities, and if we will operate on that qubit in its unconfirmed or unknown state with its probabilistic properties understood, then we can gain performance. And that's what it's all about. So we will maintain in superposition these qubits all the way through the transformations. And then at the end, we will take a measurement. And because that measurement is being taken for this particular instance, and it may have a certain probability at this point, what if we ran this thing again? We might get a different result. So one of the things we do is in quantum computing is run the same program over and over and take the aggregate answer. Under the hood, and I do want to shout out to David Merman, an author from many years ago, who's listed in my bibliography at the end, is absolutely the best book and the best treatment. It's all online as well at an archive at Cornell University, where he explains quantum computing and he explains Peter Shor's algorithm in great detail. So don't just take my word for it. I want to give you the survey here that in a classic computer, a bit can be a 0 or it can be a 1, and it's definitive in that. And we refer to that as a C-bit. A qubit, on the other hand, can be the superposition of those two states, in which case we typically give it some kind of a Greek symbol like a phi or a psi. And when we talk about its superposition, then it would be within the context over here on this line, where there's an alpha 0 coefficient applied to the 0 state. And notice the notation, a vertical line on the left and a greater than line on the right for these C-bit notations, plus alpha 1 times the 1 C-bit. And that's often expressed as a column vector of those coefficients. And what we require is that the L2 norm, or the sum of the squares of the magnitudes of the coefficients, sum up to 1. And we'll see later, if I have a column vector of 4 of these, like in a 2-qubit, that the sum of the squares of those must add up to 1. So that in effect, the square of the magnitude of that alpha is the probability associated with the existence of the qubit in a given state, for example, 0. So a single qubit we would refer to as having a 2-vector space. You can see that in the equation above. There's 2 coefficients in this vector. And if we have a 2-qubit, then we're looking at the probability of a 0, 0, a 0, 1, a 1, 0, and a 1, 1, respectively, and that would be a 4-vector space. C-bits are also qubits, and if we want to put them into that same notation, then the 0 is going to be a 1, 0. And I should have mentioned, if I go back one, that these are complex numbers. All of these alpha i's are complex numbers, so that when I say the C-bit is a qubit too, I'm actually using, just reminding us of that with the complex number notation. But you wouldn't expect it to be 1 followed by 0, but that's what it is. There's a 1 in the 0's position, and there's a 0 in the 1's position, which is how we would describe that. There are some issues with creating a quantum computer, absolutely. Noise, background noise from the environment that the quantum computer is contained in is understood to be a problem, contributing to decoherence, which is a major problem in implementing one, because the state of the qubits can deteriorate to an unintended state. So what is done in response to that is that there are error correction routines that are put into place to mitigate against the decoherence problem. So you do that and you run multiple times. We also know that state of the art requires extreme cold, and we know that they are working to improve that. So you wonder, well, okay, how do I program it? What does it mean to program it if I did? So click on this link when you get time. This will list all of the quantum computer simulators that we know to this point, or that have made themselves know, I should say. Something of a wiki here for them. So you would program these computers and you would run in a simulator, and the simulator would run on a classical computer because, you know, unless you have authorization to tap into IBM or Google or whoever is making theirs publicly available to you, you're going to run a simulator on your algorithm. But the point is that the code that you write would compile to run on the quantum computer. So you're getting the syntax right and you're running your program and you're getting the result that you would expect through this simulator. The quantum compiler then has this set of libraries where the major transformational blocks are held. So in effect, when you program, you're instantiating these transformational blocks. You're passing your qubits through transformation, rerouting, transformation, rerouting. And so when you're programming it, you are, another slide will help me explain it just a little bit better. But there are many, many programming languages available that will do this for you today. C++, Python, and Java, just among some of the ones that are most popular in that way. And you can think of an assembly language metaphor, but I think more of a object-oriented and a signal flow graph, because you can imagine the signal, the qubits coming in one after another, and each one then gets transformed, and then there's an output which is measured. And so what you're doing when you program is you're instantiating the objects in the library and establishing which is connected to which in the sense of an acyclic directed acyclic graph. Excuse me, sorry, I didn't make that more clear. And if you want a course in programming the quantum computer, there's one on brilliant.com that you can experience. Just sign up and start taking it. I think you can get a temporary free account from Brilliant with enough time to actually go through all modules of that course. And now QC programming is open source. So you can presumably download that to your own computer and compile it and run both the compiler and a simulator. Check that out. More on qubits, and I'm going to pick up the pace so that I get to the end of this in reasonable time. So we already talked about this vector notation, but the basis of it is we're going to have these 1 qubit and 2 qubit input variables, but we're also going to form our transformations out of qubits. So you can imagine a big pile of qubits that you're going to basically program like you program an FPGA, if those of you familiar with that technology. So you're just going to program it so it's wired, in effect, to take the input and produce the output. Here's the notation I described to you before with a 2 qubit, where we have an alpha 0 through an alpha 3. Based on the probability of a 0-0 or 0-1 or 1-0 or 1-1 on 2 bits of qubit. So as I said, the input register will be the qubits coming in one after another based on a clock. And the output register then is that what you're going to measure, but they arrive at the output as qubits, and then they are measured to become C-bits. And everything in between is a bunch of qubits. The logic blocks that are going to be inside here are all reversible unitary transformations designed to exploit these properties. So what do I mean by a transformation? Well, if the input is a vector, like we saw alpha 0 through alpha 3, for example, then we can transform on that vector and produce another vector on the other side. Well, as you know from linear algebra, you can form a square matrix of the same dimensions as the vector you're operating on, and it will produce a vector of that original size. And when we mean reversible, we mean we can take that output, stick it back on the input side of that transformation, and it will produce the original input. So it can come back around. That's what's meant by reversible. And in a moment, I'll go through what unitary is. The measurement blocks then are the only things that are irreversible, and they're only there at the last answer. So in effect, the last answer is made to collapse in the collapse to a real non-probabilistic result based on a measurement at the end. Okay, here it is at the bottom. A unitary matrix is a transformation, means that the inner product of the vector is preserved. And that means that the conjugate transpose equals the inverse, which is a handy feature in that an inverse is expensive to achieve, whereas a transpose is trivial, gaining performance by virtue of that restriction. So what I said about linear algebra is true. If you get a square matrix A of dimension the same as a column vector X, then we can produce a new column vector Y on that basis, and these can be cascaded. We say such a transformational matrix is orthogonal if the L2 norm of each row and each column in that matrix is 1. And we saw the L2 norm is nothing but the sum of the squares of the magnitudes of the complex numbers that form the vector. And if that is true, then the next vector will also be of the same magnitude. It'll just be rotated. For example, this in linear algebra would rotate the vector by the angle theta. And you can see for yourself that it is orthogonal. So the operators we expect to see include the exclusive OR, the inner product, the complex conjugation, all of the linear reversible unitary transformation matrices that we would operate on. So here are some that are common to complex or quantum computers. One that negates, for example, here we're operating on a 1 qubit. A controlled negate, an operator that swaps, an operator that essentially does a flip, the Hadamard, that is a combination of the other two, and then all of these qualify as logic blocks, as legitimate transformations allowed in a quantum computer. And here's a little bit more about the single qubit quantum gates, more specifically what the Hadamard is. And we note the identity matrix is going to be any of the linear reversibles times itself will produce an identity matrix. Now, these input and output qubits then are referred to as cats and there's because they are being managed and aligned as a column vector, then that makes them a ket in the literature. And we will look at signal flow diagrams. So I need to pick it up even faster here. Peter Shor's algorithm then was the observation that the way RSA works is that this N, which is the public key, is made available to anybody who can intercept. But what's behind it, what allows you to decode is the P or the Q. And so factoring the P and the Q is not trivial for large numbers, and in fact makes RSA what it is. But what Shor understood was that there was a periodicity to this, and that if we in the quantum arena, and if we could determine what that period is in the message, then we can use some fancy tricks to break RSA in quadratic time rather than exponential time. And along the way, we will use the quantum Fourier transform, a very complex logic block that is an essential component of what Peter Shor invented. And just noting here, most of you know polynomial time and exponential time. If you had a problem size 10,000 times larger than something fairly small, you have 10 to the 12 runtime, but if it were exponential, it would be 10 to the 10,000, which obviously makes it completely ridiculous. No one will ever get there. So RSA then is this notion that n is equal to PQ, and Bob wants to receive from Alice, he passes only n, but there are tricks using modular arithmetic that will let coding and decoding take place based on that n. So Eve can only intercept and decode if she really knows P or Q. But what Shor did, he said, if you could find the period R of the encoded message B, then he could directly decode B and then pull it back and get P or Q. So roadmap, use Shor to get R, the period, and then use a classical computer to find D and decode B. So again, quickly, quantum Fourier transform is this U sub ft. And here we have the Hadamard and this V, which is defined below as Vi comma J is the exponential of all this, where the I's and J's are substituted. So for example, 3, 1 would have 3 in the I position and 1 in the J position, and n sub I is a projection onto the state I. So you can see it's a complicated thing, a matrix that you're going to do, each one representing a transformation on a qubit. So with that, it's applied to the input register, and the output register is all we need. Then the number theory trick that I've already described is what's used. Here's how you would think about Shor's. Like I said, the inputs are coming here on the left. They're definitive, and they're turned into superpositions with the Hadamard. And then these U transformations are given here in this. And so a way to think about it is each one of these represents a signal flow left to right. The plus sign is where you're adding. So down from the left up to this this dot, these are summed and then carried over here to the right. This big block here on the right, which is critically important, is the inverse of the quantum Fourier transform, and forms the biggest component within this entire exercise. And here are measurements here. So when you program, essentially you're wiring up Shor's algorithm or some other algorithm as you're trying to solve in a quantum computer. The best, by far, the best explanation of Shor's is at this link, and it's David Merman's chapter on Shor's algorithm. Here's some more links that you can look at. But what about mitigation then? What are people doing about it? If it's coming, within 10 years, potentially we'll have a quantum computer at scale that can break RSA. Yeah, that's sort of the current thinking. But whether or not it's 5 or 15, none of us really knows. But here, what you'll find is that the NIST is running a competition, and they're already through 3 rounds of competition. If you'll click on each of these links, you'll see exactly where they stand, who the players are, and who the finalists are, and links to what they have proposed in their competition. So we refer to this as post-quantum cryptography, and the real randomness in it is in the quantum mechanics that would underlie these initiatives. Now, the reason these are being, this competition is about is because the NIST, and sponsorship of our federal government and with all kinds of researchers involved, have made the decision that we need to be ready. RSA is going to be blown away someday. It's been with us for decades. It's been wonderful to have it, but quantum computer is going to kill it. And we need to have encryption done in some other way. And so that's what I'm here to show you. I'm not going to click on these links. You need to go to these links yourself to see that there are many, many techniques that are being presented that will be alternatives to the current RSA, so that encryption can be restored to the community. These references, click and enjoy them. I did mention the Cornell Library of Articles on Quantum Physics is extensive, and that's the one I want to call out. David Merman's book on quantum computer science and introduction is the best I've ever seen on this topic. Very thorough, very technical. And Matt Perkypile's dissertation from Colorado Technical University is very, very informative as well, and it really kind of got me started and interested in exploring it. So my thanks to both of these grad students in helping me understand what I do at this point. Hopefully it's been helpful to you, but I think most importantly, I've given you a set of links that let you explore it further with this as an appetizer. So with that, I am done. That's how to reach me. Thank you all for attending.
All right. Thank you, Dr. Harmon. Hi, everyone. If you have any questions, please feel free to post your questions in the chat. That was a great presentation, Dr. Harmon. So we're going to give it a minute to have everyone put their questions in the chat. There was one that said, I've recently seen a sci-fi movie where a guy was programming a quantum computer and changing the past to bring her dead daughter back. Can't remember the title, unfortunately. Here's a question. Are elliptic curve schemes equally vulnerable?
I believe they are. I believe they're based on the same structure. If there's somebody, I haven't studied elliptics specifically. So if anyone, if anyone wants to contribute an answer to that, I yield. I'd say research topics on quantum computers would be in the realm of what my grad student here at the University of Denver is doing. What are these replacements for encryption? But on quantum computing itself, I'm not sure what topics I would recommend. But the literature is really, really very rich now, especially compared to 2009 when I first got interested. So hopefully those links will get you in the right direction.
Next question, what are the roles of the 1 qubit and 2 qubits used?
Yeah, so the qubits are really the manifestation of superposition, so that, they carry a probabilistic view of the state. So a 1 is just alpha 0, alpha 1 as the coefficients, and a 2 qubit would have 4 coefficients, alpha 0 through alpha 3, each of which when it is a complex number, which when in the sum of the squares of one of those vectors must equal 1. So that represents the probability that particular manifestation of the qubit, when it collapses, it represents the probability of what it is. Okay, thank you, Jeffrey, a large-scale ECC. Now you've given me something to go look for.
So it looks like there's a question from Chip Corbett. The IBM quantum computing graphical user interface was relatively easy to use, which is 2016. What is your favorite interface now?
I can't say that I have a favorite interface, but I did recognize that IBM makes available through a cloud your ability to program and run your programs through a simulator, and it's publicly available. So kudos to them. No, I don't have an opinion about whose GUI is the best.
All right. Any additional questions for Dr. Harmon? All right, Dr. Harmon, I'm not seeing any additional questions. Thank you so much again for presenting in our October CAE forum. And we will go ahead and take a quick break. We'll be back at 2 o'clock. You can stay logged on if you want to just take a break, and then we'll get started at 2 o'clock. Thanks so much, Dr. Harmon.
Thank you very much, Lauren, and to everybody on the call.